Hello everybody, Mr. Eck here, and today we're going to talk about quadratics. Now, this is a video from section 2.2 of our pre-calculus textbook, and because this is a pre-calc class, we're not going to try to cover everything that's possible to learn about quadratics in this one video. Instead, I'm assuming that you have a reasonable piece of prior knowledge, and we're going to go through some things pretty quickly and only focus on the things that would be new to us in Math 4. And because we're in a Math 4 class here, or pre-calc, I actually wanted to start with just a preview of what we're going to be learning about across the entire section so that we can use this lens as we talk about quadratics. So what are we talking about in this entire section, chapter 2? Well, the theme is about polynomial and rational graphs, and I've prepared for you 4 examples of polynomial and rational graphs right here. You may want to pause the video and just take a look at them. There's no equations there. I made these a year ago. I actually don't even know what the equations are anymore, but the idea of these general polynomial and rational graphs is they have some pretty bonkers shapes. They can look wild, but if you really focus on them, there's 3 key features that tell us what's going on with them. There are the zeros, and the intercepts. Then there's the behavior at infinity, plus and minus. And in some of them, there is behavior in the middle, called either a vertical or a horizontal asymptote. And it turns out that if you can understand in a graph like this where the zeros are, where the asymptotes are, and what is happening in the left and right ends, you pretty much know exactly what's going on with the graph, and sketching the graph becomes a connect the dots exercise. So, we are not graphing any of these today. Instead, we are going on and looking at the most basic kind of polynomial graph, and that is a quadratic. So today we're going to look at quadratic graphs and equations, both as graphs that are maybe familiar to you. We're going to try to think about them sort of as polynomials themselves so that we can use these to go forward, and we're also going to look at quadratics in some kind of word problem-y situations. So we're going to start with a little review of kind of the basics of quadratics. We would say that a quadratic is a polynomial with a simplified or general form that is ax squared plus bx plus c. So we're looking at a polynomial that we would say has degree 2. This form where you can recognize the a, b, and c, our textbook, Blitzer's Precalc, doesn't actually give this form a name. So that's kind of awkward, right? So I'll sometimes call this general form because it is kind of just the most general form you can have. I also sometimes call it polynomial form because it's the form where it looks like a degree 2 polynomial. Other textbooks call this standard form, although technically our book then calls the one we're about to learn standard form. So I don't know. Personally, I would just avoid using the word standard form because it means different things to different people in different textbooks. Or if you're ever unclear about the context of like what is a certain name for the form, just ask. It's also not that important. What is important though is if you look at a quadratic such as this, it's always going to have a graph that is a parabola. And those parabolas have a couple features. They have a vertex, which is either a minimum point or a maximum point. They have an axis of symmetry. Very important to have that axis of symmetry. And they can open upwards or they can open downwards. The thing that controls whether something opens upwards or downwards is the leading coefficient. If the leading coefficient is positive, you're going to be opening upwards. If your leading coefficient is negative, you're going to be opening downwards. Now, this general whatever form is not actually very useful for constructing the graph because it's hard to read the features from this kind of all simplified form. It's too simple. So often when you're working with a graph, you instead are working with the equation that our book calls standard form, but probably in your past, I know in other classes I teach, I've called this vertex form. Why? Well, because if you have a quadratic in this form, then the vertex is going to be at the coordinate h comma k. How do you get something into this form? You complete the square. We will probably do one later, but really a full review of completing a square has been done in other videos, so we're not going to do it here. But please go back and review if you feel like that's necessary. But the main idea then is if you have a quadratic and you recognize it in this vertex form, you can also think about it as kind of a translation or transformation. This has been translated over h units and up k units. So it links back to what we learned in chapter 1 about transformation. If you have a quadratic in standard form like this, or vertex form, it's really easy to recognize where the vertex is. It's at h comma k. But knowing the vertex for a quadratic doesn't always help you enough, right? Like if I have a random vertex, I don't know, and I say I know it's opening downwards, I don't know if it's this quadratic, or this quadratic, or this quadratic, unless I also know where the zeros are. And it turns out that vertex form is also really useful for finding the zeros of a quadratic or parabola. And here's how and why. So we're going to do 2 examples here. Give me a little more space. So for the first one, if I was finding the zeros of f of x equals negative x minus 1 quantity squared plus 4, the first thing you would do is set the whole equation equal to 0. And then I'd work to isolate the exponent here, or the term with the exponent, isolate that whole term. So I'll take away 4. And then I'm going to divide out this negative. And then you can square root both sides. Don't forget a plus or minus when you're taking the root here. So 1 plus or minus 2 will equal x, and then we can evaluate this to be negative 1 or 3. So then if I were to want to go ahead and sketch this graph, I would already know that these are the zeros. And from the vertex form, I could read the h and k as 1, 4. Remember that minus 1 means it's a shift to the right, so the vertex is going to be at 1, 4. And then just plotting that vertex and those 2 zeros is entirely enough information to sketch this entire parabola and kind of figure out its features. So that's why vertex form is so useful. Often what I see students do is they will find the vertex, and then they'll take this and like multiply it back out, right? And like simplify into ax squared plus bx plus c. And then they'll try to factor it all over again. And it takes basically a whole page of work. When if you're given that vertex form, it's going to be so much easier just to keep solving for the zeros from vertex form. Let's try another one. So here I can recognize that the vertex will be at negative 3, comma positive 1, right? So I'm doing the opposite sign of what's in the parentheses. Then I'll set this equal to 0. And start solving. Now, because we're in pre-calc section 2.2, I'm about to take a square root. And normally I would take this square root, get square root, so plus or minus the square root of minus 1 equals x plus 3. And this is normally where I'd stop and say, aha, no real solutions. But we're, like I said, in pre-calc section 2.2, so we actually know what this is now. This is going to be plus or minus I. And that's still equal to x plus 3. So then we can subtract 3 and get x is going to equal 3 plus, negative 3 plus or minus I. So the 2 zeros are going to be negative 3 plus I and negative 3 minus I. So this is an example of a quadratic that does not have real zeros. Now if I were to go to graph this, I could learn a couple things from this. One, vertex is at negative 3, 1. Okay, I should have moved that over a little more. I also see that the leading coefficient is positive, so this quadratic is going to open upwards in some way. Well, guess what? If it's opening upwards at negative 3, 1, there's no zeros. Or should I say, no real zeros. But it's still true that this quadratic has complex zeros. And that vertex form was actually really easy and useful for finding those complex zeros. So I just wanted to show you that because that is a situation that can come up sometimes. And again, what some people often will do is they'll try to multiply this whole thing out, get it in ax squared plus bx plus c form. But then to find complex zeros, they end up using the quadratic formula. And it's a whole lot of work. Instead, just keep solving, but whenever you get that square root of -1, you used to stop, you used to say, I don't know what to do with this. Now you keep going. One of the key ideas in all of Chapter 2 is that factors of a polynomial correspond to its zeros. So say that you're asked to sketch the graph of x minus 4 times x plus 2. What you might be tempted to do, and I will do it, is multiply this out into x squared, that would be minus 2x altogether, minus 8. And then start trying to complete the square or something from there. Guess what? Don't bother. Don't do it. Not needed. Why? Well, because if you know the factors of a polynomial, you know the zeros of a polynomial. And this is for quadratics, but it's also for everything else. Like all those weird functions we just looked at, your first step is almost always going to be attempting to factor those out. So if you are trying to solve x minus 4 times x plus 2 equal to 0, well, there's two options. This is called the zero product property. Either x minus 4 is equal to 0, or x plus 2 is equal to 0, right? That's the only way you can multiply two things and get 0. So that effectively means that you can split this up into two equations and solve to find the zeros, right? And if you recognize, oh my gosh, there's the zeros, you don't even have to like show all that work. You can immediately look at the factors and recognize that those are the zeros of your graph. Now, instead of trying to graph x squared minus 2x plus 8 from the vertex, now I could graph it knowing what the zeros are. So there'd be a 0 at 4 and a 0 at minus 2. I also know that this is going to open up. Why? Because there's no negative in the front, right? It's a positive leading coefficient. I don't need to multiply that out to see that. I can just look at the x's and notice there's no negatives. So then the question is, where is the vertex going to be? Well, remember how quadratics always have an axis of symmetry? Let's think about where that has to be. It has got to be directly in the middle of the zeros. So that vertex in the middle of the zeros, I want to use a different word though. I want to use the word, in mathematics, we think about middle, we think about midpoint. What we really mean is average. That is, the axis of symmetry is going to be right at the average value of the two zeros. Now, the axis of symmetry is mostly useful because it tells us exactly where the vertex is. The vertex of this quadratic, I don't know exactly where, but it had darn well better lie on the axis of symmetry. Otherwise, it would be a not very good, not very symmetric quadratic. So, let's see if we can be a little more general here. Right here, I can see that the x-coordinate is x equals 1, right? Why? Because the zeros were -4 plus 2 over 2. That's 2 over 2 is 1, right? I could take the two zeros I found, compute their average, and find it. Now, I guess let's finish solving this. So the x-coordinate of this vertex was 1. How do I find the y-coordinate? Plug in the x-coordinate. You can plug in either form. I think it's almost easier, though, to plug in the factored form. 1 minus 4 times 1 plus 2. Well, that's going to be -3, and that's going to be 3. So together, we get an x-coordinate of 9, -9. So all the way down here somewhere, 2, 4, 6, 8. I'm going to call this 9 and do kind of a weird scale. I would know my vertex of this quadratic would be right there if I'm going by 2's. So that's how we find a vertex if we're given a factored form. But guess what? We can shortcut this whole procedure. Because let's just do the same procedure, but with a generalized quadratic. So in the general quadratic form, we have ax squared plus bx plus c. The zeros of this most generalized quadratic are found by using the quadratic formula. So the zeros are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now I want to do two things. One thing is that for our purpose, this is written poorly. It's written in its sort of nicest, most compact, that's the word, form. But I'm going to split the plus or minus apart, and I'm also going to split the fraction apart, right? Like if I'm dividing by 2a across a plus sign, I can split that into two separate fractions, and I'm going to do that right now. So our first zero will be at x equals negative b over 2a plus the square root of b squared minus 4ac over 2a. I'm just taking the plus and separating it, and the second zero will be at negative b over 2a minus the square root of b squared minus 4ac all over 2a. And then I want to ask myself, well, where would the axis of symmetry be, or the x-coordinate of the vertex be? Well, say I have my two zeros. Why don't I call them x1 and x2 to represent my two zeros? The axis of symmetry would be at the average of my zeros, which would be at x1 plus x2 all over 2. But what would x1 plus x2 all over 2 be? Well, if I write it out with a little bit of copy-pasting magic, notice how the square root terms cancel out, and then we have two of these, but we're dividing by 2. So in the end, it's just going to, average of the zeros is always going to be at negative b over 2a. And this is a super useful trick. Negative b over 2a will always tell you, in a quadratic, the x-coordinate of the vertex, because it will tell you the axis of symmetry. It also reveals what the quadratic formula is really about, right? When we write the quadratic formula out like that, it's actually telling you a statement about symmetry. We never really think about it that way, because we think about it as this thing with, square roots and equations, and we don't learn it in context of graphs. But what this is really saying is that there's two zeros, x1 and x2. Somewhere in between them is the axis of symmetry, which is negative b over 2a. And the plus or minus is basically saying, okay, go a little bit to the plus side and a little bit to the minus side with this factor of b squared minus 4ac over 2a, and that'll tell you the zeros. That is, the quadratic formula is telling you that the zeros are always centered on the axis of symmetry. Fun fact. It's just an interesting way to think about it, because we never think about quadratic formula with the context of a graph. But what I've put in the box here is probably the most useful thing out of this entire section. This is a quick way to find the x-coordinate of the vertex. And if you know an x-coordinate, then you also know a y-coordinate, because you can just plug in x equals negative b over 2a, whatever that value is. And so the y-coordinate of the vertex will be, we just write it as f of negative b over 2a. So in general, then, the vertex is given by negative b over 2a for the x-coordinate, and then we just say whatever the y-coordinate is, f of negative b over 2a, plugged in. So that's like the general, very useful way to always find the vertex of a parabola if you're just kind of like looking at the standard polynomial form of that equation, and you don't have to complete the square, you don't have to do really anything if that's what you're looking for. Here's going to be, we'll do an example of this. All right, so in this one, the a is negative 1, the b is 4, and the c is 1. So the vertex x is going to be negative b, negative 4, over 2a, so 2 times negative 1. So the vertex x coordinate is going to be at 2. And then the vertex y coordinate, I'll just plug in 2. So negative 2 squared plus 4 times 2 plus 1, which is going to be negative 4 plus 8 plus 1, or 5. So I know the vertex is going to be at 2, 5. Pretty simple. It's also asking me to find the domain and the range. Once you know the vertex, you can find the domain and range pretty easily. I notice that the negative here means it's going to open down. So the domain for all polynomials is all real numbers. I'm just using the fancy symbol r for all real numbers. And the range, well, that's the y values, and it's going to start at 5 and then go down to negative infinity. Now, we always write negative infinity first. So the range is going to be negative infinity up to 5, and it touches the vertex, so we use a little bracket there. But right, once you know the vertex, it's really easy to find the range of this graph because you can kind of already anticipate its shape. Already I know the graph is going to look something like that. But I want to do one more. I want to find the zeros. So to find the zeros, I'm going to use this procedure. You could use the quadratic formula here. And if you want to use that, cool, go right ahead. I like to use the completing the square process. So to find the zeros, I'm going to first set this equal to 0. And completing the square works a lot better when you have a coefficient of 1, not negative 1. So you really want to get all the coefficients off. I'm going to divide by negative 1 everywhere. That's actually totally allowed. So we transform this into x squared minus 4x minus 1, and then negative 0 is still 0. So it kind of didn't change that. Completing the square, we're going to do minus 4x. I'm going to move that 1 to the other side, plus 1, and make a little box here, because in completing the square, I want to add something back on. So like whatever we're going to add back on to complete the square, that's where I make a space for it. What do I add back on? Well, to find that, I do b over 2a. Sorry, I just said something totally wrong. I'm not going to cut it out of the video because it's a thing that you might too get confused by. We know the vertex is at negative b over 2a. When you're completing the square, you're going to take that b value and just divide it by 2 and square it. That's what you're going to do, is you're looking for something to complete the square. So I'm going to do, that ends up being negative 2. Negative 2 and squared is 4. So it means I have to add 4 to this side. And I'll add 4 to that side. And then this becomes x minus 2 squared equals 5. Then this is going to be x minus 2 equals plus or minus the square root of 5. Don't forget your plus minus. And then x is going to be 2 plus or minus the square root of 5. So those are the zeros, and that's why I wanted to show you completing the square on this one, is that there's no way, once you see that the zeros here have that square root, there's no way that you would ever have been able to factor this. It's you know, if you have that irrational, it's really hard to factor. So completing the square or quadratic formula are what you would have had to use. Then you can, for the graphing purposes, go get the decimal equivalents of those, right? Like, make sure you include the exact answer on your paper, but for graphing, I'm going to call this 4.2 and negative 0.2. So then we can actually sketch this graph. I knew the vertex was at 2, 5. I have a vertex at about 4.2 and about negative 0.2. Does that seem symmetric? It sure does seem symmetric. And we could go ahead and put a nice graph in between. So that's the 2 plus root 5, and that's the 2 minus root 5 version of the vertex. So that's kind of a quadratic problem. Again, like, we're just graphing this polynomial, but what I like, or you know, what's good to do in Math 4 is make sure you know not just one way to graph a polynomial like this, but all the ways to approach it. So like that completing the square approach, really useful. Quadratic formula is fine, you can use that too, but you'll just want to make sure you reduce everything out. Being able to compute the vertex without having to do anything else was a really nice help, right? Like I found that without having to put it in Vertex form, and it was just very useful. I want to now spend a little bit of time exploring this idea that factors and zeros are linked. This isn't probably going to come up on the homework in this section, but it is a huge theme of Chapter 2. So kind of exploring these themes. And here's the generalized statement that I just really think you should get, into your heart right now, which is that if a quadratic polynomial has a 0 at x equals a, then its equation has a factor of x minus a, right? Like if you know the 0, you actually know a piece of its equation. And what's cool about this is this says quadratic polynomial, but I could just as easily scratch that out, and this is true for every polynomial. So getting this idea in about zeros and how they're related to factors is a really, really useful thing. And that's what I want to bring it in a little early. It also lets us have some complex number fun time. That's what I'm calling this section. If we have this idea, I'll try to keep them both on the screen here, that zeros and factors are linked, then if I tell you that a parabola has complex imaginary zeros of plus or minus 3i, and remember what that means. It means that it's either opening up above the axis or opening down below the axis. We would have no clues about this, right? Like we don't know where it is in the axis. We don't know where to put this thing. Well, guess what? We can still write its equation, or at least a possible equation. Now, you could have different coefficients, of course, and stuff, but here's how. If the zeros are x equals 3i and x equals negative 3i, those are the zeros, then this little thing that I'm going to call the factor theorem says that the factors are going to be x minus that and x minus that. So an x minus minus 3i, I actually write it out. So an equation for this parabola actually is pretty easy to find. Because all you have to do, that becomes a plus, is multiply out your factors. So then this is x squared minus 3ix plus 3ix. I'm just treating the I like a variable for now. Minus 9, 3 squared, I squared. Oh, whoa. Let's do some simplifying. 3ix minus and 3ix plus will reduce out because of addition. I squared is equal to negative 1. That's the main definition of I, is that when you square it, you get negative 1. So what do we get? X squared plus 9. As a parabola that has complex zeros of plus or minus 3i. Now, technically, what I could probably have done is put a coefficient on here, and then it could have been, any quadratic with the coefficient a x squared plus 9 would also have the same zeros. And you'd need a little more information to solve for that coefficient. But in general, that's how you use factors to find equations, is you just set them up and multiply them out. Even if those factors are imaginary, which is super cool. We can even keep playing this game. I really like to do this now just because this is a tricky idea, and we're going to see it again in a couple sections, but then when we see it again, it's going to go by super fast, and there's a lot of other things going on. So now is a really good time to start thinking about zeros in this way. Say that a parabola had zeros of 1 plus or minus 3i. So then the zeros, to write them out really explicitly, would be 1 plus 3i and 1 minus 3i. So then the factors are always of the form x minus the 0 then you can simplify. And I'm not going to put any coefficients on the front. This would be if you're really trying to be, saucy. You put a coefficient out there so you can solve for that too. Now you just have to multiply those out. There's a couple tricks for multiplying them out, like of how you group your terms into difference of squares, but you can also just make a dang darn box, and that's what I'm going to do today. Here's what I mean by box. X minus 1 minus 3i, x minus 1 plus 3i. Right, so we'll just multiply it out. So we get an x squared minus x. Here's a 3ix. Here's a minus x. Here's a minus 3ix. Here's a 1. Here's a minus 3i. Here's a minus minus 3i, so that's a plus 3i. And then here's a 9i squared, minus 9i squared. So it looks like some things are going to reduce out. Minus 3ix and plus 3ix, minus 3i plus 3i. The minus x's don't cancel out though, right? Those are both minus x's, so that's something to look for. So let's group all this up into x squared minus 2x plus 1 minus 9i squared. But wait, I squared is minus 1, so this is really like plus 9. So this is really x squared minus 2x plus 10. And to check your work, what you could do is either complete the square or plug this thing back into the quadratic formula, but you would recognize that it has those magical zeros. So you can use even imaginary zeros to build a quadratic that has those zeros as factors. One thing to watch out for really is this. Just make sure, if you're going to do this, that you set up your factors correctly. Factors are always of the form x minus, so that doesn't show up, x minus something, and then you put the 0 in, and then you can start to simplify. So just watch out for that. This concludes Complex Number Fun Time. I hope you've enjoyed it. Working with imaginary zeros is just, the more you do it, the more comfortable you'll be with it, and the happier you're going to be when it shows up in the middle of a problem. But we're in big kid math now. Like when we want to solve something, we really want to solve it. We don't want to just quit because the answers aren't real numbers. We want to keep going. So for the last part of the video, I want to talk about modeling problems, which you also probably call word problems. And a lot of people are scared of word problems. They see, oh my gosh, why are there words in my algebra? And they freeze up. But really, you shouldn't be afraid of them. The math contained within all of these word problems really just is quadratics. So there's a couple different flavors of problem we're going to look at. I'm going to show you how to do each flavor of problem for a basic approach. They all share the same overwhelming approach. And at the end, you're going to end up, in each problem, you end up with a quadratic that you're going to find the vertex for. That's why they fit really well into this section. So it's a little strange that we're doing word problems. We're generally doing pretty, pure math stuff, but this is our little nod to these modeling problems. Now for these problems in general, here's the approach. 1, we're going to identify a variable very specifically. We're going to be really sure what our variable is. Then, often these problems will have a second variable. But when we create that second variable, we want to relate it to the first variable, right? These aren't going to be two separate things. They're going to be things related to each other. Then we're going to end up creating a function that's called an objective function that we want to minimize or maximize. That's going to be our objective. And that objective function will have just one variable. So we're going to be going from many variables down to one to try to create an equation that models the situation. That's why we call it modeling problems. And at the very end, like I said, we're going to use negative b over 2a for that vertex. And that's going to help us maximize or minimize the thing we're looking at. So, modeling problems. Let's start with, it's kind of a mathy modeling problem, but I really enjoy these. So here we go. Among all pairs of numbers whose difference is 8, find a pair whose product is as small as possible. What is the minimum product? So you might start approaching this problem, especially at first, by just taking some numbers and guessing and checking. So how about 2 and 10, right? So difference is 8, means they're 8 apart. So 2 times 10 is 20. Can anyone do better? Well, how about 1 times 9? Oh, well, that product is 9. Their difference is 8. What about 0 times 8? Oh, that's 0, right? Obviously, the answer is 0 and 8. We're looking for the product that's as small as possible. But the key word here is numbers, not whole numbers. Numbers means probably real numbers, right? So we have to be thinking about everything. It actually probably could include complex numbers, but it's going to end up being restricted to the reals. And so, for example, like what about -4, let's do -2 and 6. That product would be -12. Well, guess what? 12 is bigger than 0, but -12 is smaller than 0. So we're going to have to figure out, like, how do we get this? How do we get this product as small as possible? And how can we be sure? How can we be guaranteed that, even if we think we know that the product is, maybe we can guess and check, maybe -4 and 4 gives us -16. That feels pretty small, right? I can't think of anything smaller, but what if it's really -4.1 and positive 3.9, right? Like, how can I prove that my answer is the smallest? So to prove that, we're going to have to use quadratics. Okay, so guess and checking is out of the way, but that was helpful because it helped me recognize that I'm thinking about a much larger set of numbers. So I'm going to need to do some equations. So I said first that we're going to define a variable. I don't care what name you use for variables, but x and y are very popular these days, I've heard. So I'm going to say let x be, and I just wrote that because that's how every problem is going to start, no matter what the situation is. And here, I think it makes sense, just let x be the larger of your two numbers. It doesn't have to be the larger one, but it helps to be a little more specific. And then we'll let y be the smaller one. We know their difference has to be 8, so they can't be the same, right? So if they're not the same, you're allowed to say, well, one's smaller than the other, or larger than the other. I also need to state what I mean by difference is 8. So difference is 8 would mean that the bigger one minus the smaller one would equal 8, right? Big minus small equals 8. So this is going to be what I consider an equation relating x and y. But it's not what I'm trying to maximize or minimize. So I also need to write an equation that represents the thing that I'm trying to, the question. Like, what am I trying to do here? And the question here is, what is the minimum product? So I need to also come up with an equation or an objective function that's going to represent the product. So here I'm going to write the product, I'm going to use P for product. The product of x comma y, and in this case, it's just x times y. And this is what I'm trying to minimize. Now, we have found ourselves a multivariable calculus problem because what we really have here is like a z equals xy. And guess what? If you have 3 variables, are we really graphing in 3 dimensions right now? No, we're not. So this is not an equation we know how to maximize yet. So what we're going to do is turn this from a 3 variable situation where we have product, P, x, and y, into something where we just have P and x, right? We just want P of x. That's going to be our goal. We need to eliminate y. How are we going to do it? Substitution. So I got to take my first equation that relates x and y and use it to get rid of the y, basically. So if I want to get rid of y, I need to solve for it. So this would solve for adding y and taking away 8, that y is x minus 8, right? That makes sense, that the smaller number, if you have the bigger number, you take away 8, you should get the smaller number. So if I substitute this in here, then the product in terms of just x, oh, there we go, is x times x minus 8. Notice what we have now. we have a quadratic, right? This, oh my gosh, is a quadratic. Being really careful, I need some space here. It's not a quadratic in terms of x and y. Like if I was to graph this on the axis, I would have x and p of x, right? The product is actually the second variable. But that doesn't matter. It doesn't matter what my axes are called. I know what to do with a quadratic. Let's multiply it out. X squared minus 8x. I'm looking for the vertex, right? So I want to minimize the product, right? P of x is the product. I want to minimize it. Well, this is going to be some quadratic. It has zeros at 0 and 8. So the minimum product will be at the vertex. So where will the vertex be? Well, we know it's going to be at negative b over 2a, which is going to be positive 8 over 2, or 4, equals x, right? So at x equals 4, that's the proven vertex. Now, let's go back and look at the question. It's actually a many-step question. It said, find a pair of numbers and what is the product? So I've only solved the first part. I've just solved for x. So now I need to also find y. But I already solved that y is equal to x minus 8. So then y will be 4 minus 8, or negative 4. So that's my y. And it said, what is the product? Well, the product, now that I know x and y, I can just use this original equation, is going to be x times y. 4 times negative 4 equals negative 16. So what have we shown? We've shown that in a problem such as this, where we're finding a pair whose product is as small as possible, the two numbers that give us the product are 4 and minus 4, and the smallest possible product of those numbers is negative 16. I really want to emphasize that it's important to use the quadratic equation approach here, or not the quadratic formula, but just a general quadratic approach, because these can be tricky, right? So like this worked out really nicely, and we were able to guess and check the answer before we did all the justification. But I can make these problems a lot harder. In fact, the easiest way to make a problem like this harder is to cross out that 8 and write a 9. Now all of a sudden, I know that the answer, I think it's going to be 4.5 and negative 4.5. But like you probably won't guess and check your way into that. Another way I could change this and is make it not difference, but sum. That would change the problem. Right? So there's a lot of different ways that we can mess with this. And once we start messing with it and making it a little trickier, you really, really, really need a quadratic equation type of approach. So again, in problems like this, easily or define your variables really precisely, relate the variables together, decide what your objective is, what are you trying to minimize, and then substitute around until you can actually do it. And then you'll be able to solve problems like this. We got 2 more problems, and they are actually really, really similar to this first one, but they're very different contexts. So the next one, and again, this is kind of the most basic version of this problem you'll ever see, and most of the ones you see on homework and stuff are going to be harder than this. So make sure that you know how to do the basics, but don't rely on this problem being problems you see being quite as simple as this one. So this problem says you have 120 feet of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area. What is the maximum area? Again, we could start with just a little exploration. You might say, all right, do I want a long, skinny fence? Do I want 10 feet, and then 50 and 50, right? Is that what I want? And you could figure out what would the area of that be. So that would be, nope, it'd be 500, right? Like that'd be one possibility. Do I want to do something a little more rectangular? Do I want to do a perfect, exact square? And you could guess and check all of these possibilities, but it's going to be easier to just do some algebra. So I'm going to make a generalized rectangular region, and here again, there's no variables, so we got to create some variables, right? And like you get to choose. I think this is the stage where a lot of people freeze up on word problems. Is there's nothing in here that says what my x is or what my y is. You have to choose it. So choose wisely. And guess what though? If you make a bad choice and the problem doesn't work, go back to the start and pick different variables and see if that works better, right? The best thing you can do on a problem like this is just try something. So I'm going to say that x is, the vertical side, length, and we'll put that on here, x, y is the horizontal side length. Y. Now I want to see what kind of relationships I can construct between x and y. I want to think about the objective. The objective is what is the maximum area. So the area, now that I have variables, in terms of x and y, is going to be length times width, x times y. So that's what I'm trying to maximize. But I can't do it yet because I can't maximize a 3-variable function, right? I have a, x, and y. That's too many variables for me to deal with. So now I'm going to go back over here and start looking for relationships between x and y. Well, the main relationship that I see that I haven't used yet is this fact that we have 120 feet of fencing. So if I look at the perimeter then I would know that x plus y plus x plus y, all the sides added up, would have to equal 120. Simplifying a little bit. Dividing by 2. And then I want to think about what I'm trying to do. I'm trying to maybe solve for x. I'm trying to solve for one of the two sides. It doesn't really matter which. So I need to isolate the other side and eliminate it. So I'm going to say, all right, I want to eliminate that y by solving for it. So we'll say that y is equal to 60 minus x. By the way, you can also go right back into the diagram and mark that in. I really like to do that because it helps me visualize the situation. Say, okay, I have x, and then the other side is related to x as well. So then the area now, in terms of just x, would be x times 60 minus x, which I could simplify to negative x squared plus 60x. I'm both distributing and reordering to make it make a little more sense. Now let's think about what this is. This is a quadratic. Where the axis labels would be x and area. So the y value is not appearing in this quadratic. It's x and area. It would be opening downward. It would kind of start at 0 and come out to here. It would be opening downward, which means that, like, basically that means if my corral gets too long and skinny in either direction, the area is approaching 0. So I want the vertex, right? The area will be maximized at the vertex. So what do I do to find the vertex? I do negative b over 2a, just like all the other times. So negative 60 over negative 2 ends up being 30. That will be the x-coordinate of the vertex. So I can put that kind of on this graph. And then I can start to also fill this back in to the diagram. Right? In the previous problem, I didn't have a picture, but now I do. If x is 30, this x is also 30. 60 minus x, so 60 minus 30 is also equal to 30. And y here is also equal to 30. So the dimensions are 30 by 30 for an area of 900. Couple things. One, pretty cool, right? Two, you may notice that this is a square. right? Like it's secretly, I drew it, I didn't assume it was a square, but it ended up being a square. And that's kind of generally a true fact. Like if you want to maximize your area or volume, a cube, for example, is a really nice, perfect volume because it's the perfect balance of length, width, and height. But don't get so excited saying, well, every time I see a problem like this, the answer is going to be a square. Because what's next? Well, the next thing that I would do to you is say you still have 120 feet of fencing. But maybe now you have goats and pigs, and you have to keep your goats separate from your pigs. So you have to take your 120 feet of fencing. Oops, sorry, that little blackout there. That's really frustrating. So you have to take your 120 feet of fencing and do something like this to it. Divide it down the middle. Now, if you were doing a problem like this, I would still let your x's and y's be the same. Let your vertical sides be x and your horizontal sides be y. But notice how here we'd have 3 x's. So our equation we set up would be something like 2y plus 3x equals 120. And then you could still solve as normal, and you'd end up with y equals 120 minus 3x over 2, and then your area would be x times 120 minus 3x over 2. And you and solve this. I'm not going to do this because I think it's almost exactly a homework problem, but notice how it gets more complicated. The key in a problem like this is get a good picture first and assign some nice variables and make sure you account for them. But once you have your variables in your picture, everything still works out nicely. Another thing that we might do, I've seen versions like this, is they say, imagine there's a little river. And you're making your fence for your happy cows by the river. Well then, you could have x be your vertical side and y be your horizontal side, but you set up your equation, you only need one x, and you can solve, right? So like, there's a lot of different variations based on what you might see, but it's just make a good picture, kind of work out with these. They're all going to pretty much solve in the same way, making that objective function, then maximizing it. This last class of problem is the one that really trips people up. And I would call this general class a revenue problem. Basically, we're trying to sell something, we're trying to maximize our revenue. So here's the story. I sell these, I don't, but pretend I do, these cute little decorative trees on Etsy. In a given month, I can sell 50 of these little trees at $20 each, right? Pretty good. And I can even, let me calculate that. So that would be, in 1 month, it'd be 50 times 20, which would be, is that a whole $1,000? I could make $1,000. But I want to know, like, can I do better than that, right? I need some more, I want to see if I can improve my revenue. There's a couple ways I can do it. Of course, I could make my trees for cheaper. But I'm not going to do that. Instead, I'm going to see what happens if I raise my prices. Well, supply and demand says that when you raise your prices, probably fewer people are going to buy your little trees. And so say I did some market research that if I raise the price by $5, I will sell 2 fewer trees. This is just from a survey of tree purchasers. I know that if I raise the price by too much, I would not sell any trees, right? If I raise the price by $100, then I would sell 50 times that fewer trees, and I'd sell no trees, right? We can't sell no trees. That'd give me no dollars. So that's probably not it. But what I want to know is what the maximum amount of money I can make is. How many trees do I need to sell? How much should I charge per tree? And how much money will I make if I do this plan? So it might help in a problem like this, especially when you're first starting out, is to think about, not even try to assign variables, but to just explore the numbers. So let me see. I'm going to make an in-out table. Maybe price, trees, sold and the revenue. And again, this table is not a justification for a final answer, right? Like, don't give me this table on as your work on a quiz. You can make one and put it on the side, and I'm happy to look at it. But this is just for you or me to explore. So if the price is 20, but I sell 50 trees, then I would make $1,000. That's what I said before. How am I calculating the revenue, by the way? The revenue is always the price times the number sold. And this is the thing that I'm going to be trying to maximize. So it's nice that I've already kind of got an idea for how to calculate that. All right, so it said if I raise the price by $5, so that'd be $25. I would sell 2 fewer trees. That'd be 48 trees. So I have to do... Whoa there. Not that. 25 by 48. Oh, that would give me $1,200. So it seems like with just a little change, I can make a lot more money. What if I do it again? So $30, I would sell 46 trees. That's going to be even bigger, right? $1,380. And I can sort of see where this is going. What if I went all the way down to, I don't know, $100? Let's see if I can get a maximum. Now, I actually am curious, how many trees would I sell here? I guess I might be looking for how many times did I increase the price. So I had to do, it's an $80 difference times 5 each. So I think that's 40 price increases. Is that right? No, it's like 16 price increases, right? I had to go 16 times, so I'll sell 16 times 2 fewer trees. I should be selling 32 trees here. Sorry, I had to pause for a second there. It looks like if I sell trees at $100, I'll only sell 18, but I'll make $1,800. But I can imagine at some point, right? Could I sell a $500 tree? No, because I'd sell none of them. So eventually this product price is going to have to go back down. And you can imagine then that the revenue is taking a quadratic path. Eventually, our prices will be too high. Now, where is that point? That's where we need to use some math to figure this out. So completing this whole table is not going to be the efficient way to do it. Instead, let's think about how we could set things up. Now, when I made the table, I think I noticed one key thing. And this is going to be the big star here. Both of the price and the trees sold were depended on the number of increases I made, right? Like, am I setting... When I looked at my market research, the market research told me that every $5 I sold 2 fewer trees. So to kind of think about that as the unit. So in a problem like this, the smartest move and the way that gets this to work, because a lot of people try to set up the variable to be like X equals trees and Y equals price. But the thing is they're really related through this secret variable of the number of increases. So check this out. Let X be the number of price increases. And it seems counterintuitive, but look at what happens. Then the revenue is going to be the number sold times the price for each. And it turns out that I can create an equation for the number sold and an equation for the price each in terms of that X. So I don't need to make a bunch of other complicated variables. The number sold is going to be 50 trees minus 2 times the number of increases, right? Every time I increase the price, I sell fewer trees. So that's an easy linear equation for the number sold. The price each was $20 plus 5 times the number of times I increase the price. Every time I increase the price by 5, I'm increasing the price from 20, so 20 plus 5x. That's a quadratic that represents our revenue. And you'll notice too that you have this interesting thing where you're going to have like a minus something and a plus something, because you have your x variables have to be in tension, right? One's kind of pulling and one's pushing. You're pushing the price up, but you're pulling the customers down. That's what's going to make this eventually turn around. All right, so let me make this a little bigger, and let's see if we can work with this quadratic. It's going to be a lot easier than working with the table. So we should distribute everything out, right? I want this to be in that polynomial form so I can find the vertex. So doing the quadratic and then simplifying a little bit. And this tells me my revenue curve. So I notice again that it is opening downwards, which means eventually my revenue, right, if this is the x and this is the revenue, eventually that's going to fall back down. So where will it be at its maximum? Well, it'll be at its maximum at the vertex. So let's do negative b over 2a is negative 210 over 2 times negative 10 is negative 20. I know it's going to be positive. 10.5. Now, something interesting has happened here also, which is that the vertex happens at 10.5. It's not clear in the problem if I'm allowed to increase the price half a time. So I may round this either because it's 0.5, I'll round to 11. I would round to the nearest whole number of price increases. In this case, 0.5, you could actually go either way, but I'll round to 11 increases. And then I'm going to plug this in. So the revenue, I'm going to plug it in where? To this equation right here. So the revenue is 50 minus 2 times 11 times 20 plus 5 times 11, 20. Simplifying that, 50 minus 22 is 28, and that is 20 plus 55 is 65, 75. Or about $2,100. So in this case, if I sell 28, and let's look at what this meant. This was the number of trees. So 28 trees at a price of $75 each for a total revenue of $2,100. And I've proved that that's the maximum by computing the vertex. So it turns out in my table, when I set the price at 100, I'd actually gone all the way past the maximum, right? It looked like I was still going up, but the most money can be made somewhere in the middle. And how do you prove it? You use that quadratic. So this is a really tricky type of problem. Folks will struggle with it. The best way to get over your fear is just to do them. Keep trying problems like this. Be very cautious in how you set up your variables. But again, my big tip to you is always, if you can, let it be trees. Don't let x be not trees, and don't let x be like the price itself. Let it be the number of increases, because you can then kind of think about a flowchart, right? You can say, all right, I can relate the trees and the price back to that x, right? So you kind of got to think about what's the top level thing that you're controlling, and then both the trees and the money tell you the revenue. So think about what the top level thing of control is here. All right. Well, this has been quite a long video. Thanks for sticking with me for so long. We are pretty much done. I want to give you just a little philosophical word on these modeling problems. They're a little strange, and we spent a lot of time doing them, but they're not really related to how we study polynomials in this unit. Like, we're not going to go back and do modeling problems in every section. They're really just here. But why do we do them? Well, they're perfect for ACT and SAT. Each of those three things felt almost exactly like an ACT problem. Maybe not that last one would be super hard, but the volume of a pen, that's like ripped from the pages of the standardized test. So people are always asking me for test prep. Here's a really good one. 2, these are really, really similar to the problems you'll see on the AP Calc exam. AP Calc has a lot of these longer, setting things up, figuring out what the variables are, what's constant, what's given, and what do you need to maximize or minimize. In Calc, you do this in 3D. So a very famous calculus problem that any Calc student or teacher knows about is the soda can problem, where you're trying to maximize the amount of soda you can fit in a can for the minimum amount of material used to create the can, because aluminum is like expensive. And it's a little harder in 3 dimensions to do this, but it's totally a problem that you'll do, and you have to set up your variables in a really similar way to these problems we've done just above. So this is really good practice for like kind of future things, even if it doesn't seem related to what we're doing right now. Okay, this is it. This is the end. Just to summarize, here's our 3 big new ideas about quadratics for this unit. You know a lot about quadratics already. First thing, the vertex of the quadratic, x-coordinate, is always at -b/2a. So useful. All the time you can use this to kind of get around, avoid having to do all kinds of messy factoring. So very useful thing. Thing 2, if you have a 0, that correlates with a factor of a quadratic, or not just a quadratic, but any polynomial. 0 of 3 means you had a factor of x minus 3. And that's true for imaginary numbers also. Which is great. It's another way for us to work with those imaginary numbers. Thing 3 is those word problems. You can optimize some functions by making an area, making a product, and if you can identify some secret quadratic formula in there, not the quadratic formula, but some quadratic equation in there, you can use our first fact about the x-coordinate vertex to do all kinds of solving and minimizing and maximizing. So really useful things with quadratics. Thanks for sticking around. This went a lot longer, a little bit longer than I thought, but it's really good to look at these quadratics in a thorough and complicated way. Even though you think you might know about them, you don't know all of their secrets quite yet. Good luck on your homework problems. Let me know what questions you have. You've been watching ECMath. Have a lovely day.